Hi and welcome back to another lecture on number systems. This is a continuation of the previous session on number systems, which was lesson 1. This is lesson 2. My name is Dr. Ritesh Shajira. As a recap, looking at what we've just spoken about in the previous lesson, positional notation can be expressed as a formula, and the formula is given by this over here, where D is your digit in the ith position of the number, R is the base of the number, N is the number of digits in the number, your I is the ones in between which tell us about which digit are we talking about. So in the previous lesson, we were really taking a lot of time to represent the number 642. And I hope by now you understand what this means in base 10. Usually we denote the base at the bottom like this. So we denote powers at the top, but the base we would denote at the bottom. The number 642, we took for quite a ride in the previous lesson, and we tried to represent this in different kinds of bases, trying to really understand what it means for this number to be represented in base 10. So in this lesson, we will continue to explore number systems as well as how to perform certain operations in different number systems like base 2, base 3, and so on. So let's look at this number 642. If we were to represent this number 642 in base 10, then we would simply say, using this positional notation formula, we could say 6 multiplied by 10 to the power of 2 plus 4 multiplied by 10 to the power of 1 plus 2 multiplied by 10 to the power of 0. Well, so if this is the number in base 10, well, as we saw from the previous lecture, that in that table where we saw where the column was the different bases and the rows were the values in those bases, we saw that we could actually express a particular number in the different bases. So for example, if you're converting the number 1 in binary to another number in base 10, then that 1 would be translated from binary to 3 in base 10. The number 2 in decimal, which is aka another word for base 10, can be represented in binary as 10. The number 4 in base 10, a decimal, can be represented as 100 in binary. So if you remember that from the previous lecture, then you would already now understand that we can move from base to base by converting a number from one base to another. And so just to give you a taste of that, have a look at these examples of this number 1202, which is a number in base 8, 1202. But if we want to convert it to base 10, we can just put it in this formula. So it becomes 1 multiplied by 8 to the power of 3 plus 2 multiplied by 8 to the power of 2 plus 0 multiplied by 8 to the power of 1 plus 2. We also times 8 to the power of 0. We would get this number. If you put this in your calculator, you would get 642. Similarly, if this is a base 8 number, similarly in base 2, if you try the same positional notation formula with a base 2 number, taking this base 2 number, for example, which is 101000010, and convert it to base 10, by putting it in the positional notation formula, you will still get 642. So this is a nice example of how very transparently we can go from one base to the other using the positional notation formula. Okay, so that brings us to operations in different bases. So before we spoke about what are different base systems, what were the symbols involved in using different base systems, we found that in some bases, because we ran out of symbols, we had to borrow letters from the alphabet to serve as our symbols. But in this part of this lecture, we'll look at different operations in different bases. So let's start with base 2. Now obviously everything I teach you in base 2 can be applied to other bases. You can be doing operations in base 3, addition in base 4, addition in base 5, subtraction in base 6, exponent. You can do logarithms in any base as well. Any operation you could do in base 10, you can also do in base n. So let's start with arithmetic just to give you a taste of this. And once you understand arithmetic in base 2, you will be able to transfer this knowledge to the other bases as well. So while you are doing arithmetic in base 2, think about, and I'll try to help you think about how you can transfer that knowledge across to other base manipulations in arithmetic. Right, so let's start looking at addition in base 2. In base 2, we want to add two numbers. So obviously, if we're doing arithmetic in base 2, the numbers will be represented in base 2 as well. So we have two numbers. The first number is 1010111, and the second number is 1001011. And we are asked to add these two numbers together. Well, remember that if you were doing addition in base 10, as you did in primary school, when you add two numbers together, if you have an overflow of a digit, what did you do before? You simply carried it on to the other side. You carry it to the 10th position, if you remember that. So there is a difference there. So, okay, great. So in base 10, if you're adding 6 and 5, for example, in the same column, what would you do? Well, you would get, adding 5 and 6, sorry, what would you do? Well, you'll get 11. So the 1 will be carried to the next column and the other one would go down as a remainder. So similarly, this works in base 2 as well. Okay, great. So let's look at this. So you can ignore this. I've just put it here, the carry value, so that you can see it. But this is our first number and we're adding it. We're adding it to the second number. Okay, so you can ignore this for now. Just look at this. This is the first number, adding it to the second number. So let's start with this column over here. So it becomes 1 plus 1. 1 plus 1. 1 plus 1, okay, in binary is 1 0. Okay, 1 0 occupies two spaces. So there's a carry. So we need to take that first digit and put it as a carry value in the next column. So that 1 goes here. Okay, 1 0 was the answer, so the 0 would come down here. So 1 plus 1 is 1 0. The 1 gets carried, the 0 comes down. Okay, now I've got the 1 here I've carried. So I've got to start adding from this one. So 1 plus 1 plus 1 gives us 1 1. So 1 1, the 1 gets carried, the 1 gets put down. Okay, so the carried value, I start adding from the carried value. 1 plus 1 plus 0 is 1 0. Okay, and if you want to in your head, you can think that 1 plus 1 is 2 and you convert it to binary, which gives you 1 0. Okay, it works as well. So there you get your 1 0. And we've got a carry, so if we can say 1 plus 1 is 1 0 again, carry the 1, put the 0 down. 1 plus 1 plus 0 is 1 0, so you carry the 1, put the 0 down. 1 plus 0 is 1. 0, so there was no carry, okay, so we notify there's no carry. You could have left it blank as well, that's fine, but I want to explicitly show you that there's no carry. It becomes 0 plus 1, which gives you 1 0, and that's 2. So there's still a carry here. We're not yet done, and there's a 0 here and there's a 0 here. So that's 0. So it's 1 plus 0, which is 1, and this is your answer. This answer is the addition of these two numbers, this one and this one. And you see there are carry values involved as well. So this is very similar to how you would do addition in your base 10. And this is the same way you'll do it in base 3, the same way you'll do it in base 4 and base 5 and any other base. It's the same principle. There are carries and there are and you just have to include the carry when doing the next column addition. So let's look at now subtraction in binary. So now that you know how to do addition, if you didn't understand that, go back and Try to look at it and figure it out. It's not difficult. And to also try to make up your own examples. The main thing to understand is that when you have two digits, there is a carry that needs to be taken over. So let's look at subtraction in binary. Subtraction is also very simple. You got two numbers. This is your first number, 1, 1, 1, 0, 1, 1. And you are taking it away from 1, 0, 1, 0, 1, 1, 1. So let's see how to do this. Well, here's your first number, okay, from the previous slide. So you are take this away from this. So this becomes your A minus your B. Okay, so this is the top item because you are taking this away from this. Okay, so this is your this will become the top value minus this value over here. Okay, sorry about that. It's a clarity, right? So this is your value that you're taking this value away from this. So here it is. You're taking this value away from this. I think the wording of this question might have confused some of you. So in just try to take note of the wording so you know which one comes first. Okay, a very simple way of just saying would be in a test, for example, I could just say, what is this minus this? And that'll be easier. But take note of the wording. I mean, it is important to pay attention to these things. So you've got this number and you are subtracting this number away. All right, you're taking away this. So it's this minus this. And now we've got to do the subtraction. So let's see how this actually works. We're going to do this together. We'll start here. Ignore these things. We're going to get there. So it's 1 minus 1. All right, that's easy. That's just 0. 1 minus 1, again, that's just 0. That's easy. 1 minus 0. Well, that's easy too. It's just going to become 1. Now you've got 0 minus 1. Now you remember from base 10 subtraction that if you are going to subtract when you don't have enough, what do you need to do? You need to borrow. You've got to go and borrow from the friend next door. So what do? You borrow. This now becomes this. You borrow a unit. 1 unit here is 2 units here because of the nature of the positions. So you borrow this. This now goes away. This 1 goes away. And there's nothing left. So you mark a 0, indicating that there's nothing left. And you borrow, because 1 digit here is 2 units here, what in actual fact you are moving across is the 2 units. So you are borrowing 2 things. You're borrowing 1 thing in this column, but it becomes 2 things in this column because of the nature of moving from one column to the other. Remember that these positions aren't just numbers. They are units. There's hundreds and tens and thousands and 10,000s and hundreds of thousands and so on. In this binary, it's the same principle. 1 unit and then 2 units on the next side, and 4 units in the following side, and there's powers of 2 as well. So you are moving this 1 over to give us 2, and the 2 minus 1 is 1. Okay. Now on this side here, since we once we borrowed away this 1, we have a 0 here. So this 0, we don't have enough to subtract the 1. So what do? We borrow. But where do we borrow from? Because if we go next door, there is nothing to take away. But there is something to take away the next door after that. So we borrow from this 1. It becomes 2 units on this side. And then we borrow again from the 2 units on this side. Okay, so we have 1 left over on this column. It gives us 2 units on this column. And we can say 2 minus 1 is 1. And 1 minus 1 is 0. And then we're done. So this might have looked complicated, but if you, like I said before, you can go back. This is a video. You can go back and hear the explanation again. And so this is the answer. Same concept with base 3, same concept with base 4, and all of the other bases. Only in base 2 you borrow, you're moving 2 units across. In base 3 you'd get 3 units. In base 4 you'd get 4 units. So only in base 2 you're getting 2 units here. In base 10 you'd get 10 units, and you're used to base 10. So that is a very nice way of doing subtraction and addition in a certain base. But now going back to the bigger picture of converting between bases, it turns out that there's a special relationship, there's a power relationship between certain bases. And binary and octal is an example of two bases that have this power relationship. So you have to ask yourself, what power of 2 will give you 8? If you're looking at the power relationship between binary and hexadecimal, you'd ask yourself, what power of 2 gives you 16? What power of 2 gives you 32? And if there is a power between two bases that exists, then that'll give you an easier way of converting from one base to the other. And I always like asking questions like this in exams, because you must try to find the easiest way to move from one base to the other. In this example, if there are power relationships that exist between bases, then you can simply directly convert from one base to the other. Okay, let's have a look at how this works. So the idea is to mark groups of 3 because 2 to the power of 3 gives you 8. So that's why we'll be marking in groups of 3. If this was 16, if we're moving from binary to hexadecimal, we would mark in groups of 4 because 2 to the power of 4 gives you 16. Okay, from the right. Okay, this is because 3 binary digits exactly represents the octal digit. And I don't know if you remember this from the diagram in the previous lecture, but if you didn't, that's not a problem. If you didn't notice it then, it's not a problem. You just have to remember that 3 binary digits, because of this power relationship, 3 binary digits, because 2 to the power of 3 is equal to 8, 3 binary digits exactly represents one octal digit. Okay, so these are your octal digits, 0, 1, 2, 3, 4, 5, 6, 7, and 3 binary digits represents each octal. So here, 000 represents this 0. 001 represents this 1. 010 represents this 2. 011 represents this 3. 100 represents that 4. 101 represents that 5. 110 represents the 6. And 111 represents the 7. So if I ask you, convert this number to octal, okay, then you're going to group in 3s. You're going to start here. Here's a group of 3. You're starting from the right. Here's a group of 3. Here's another group of 3. You write it down. Here's the last group of 3. Imagine there's a 0 here, so that'll give you a group of 3 as well. That's this. Okay, and you can directly convert using this to octal. So this is your binary value converting to octal. You take it, you group it into 3s, and from that directly convert into your desired base, which is now octal. So 011, looking back at this, 3 was represented by this. So you look for this number, here it is, it's a 3. 101 is a 5, using this. You can do this neater in a table if you like, just matching them up. And then 010 is a 2. And so you've directly converted from this number in binary to this number in octal, in base 8 octal. Okay, remember that I'm only showing you this for one case, but you can generalize. You can go from powers of 2, you can even look for powers of 4. You can even look for powers of 6, powers of 5. You can convert easily from base 5 to 25 by grouping in 2s. You can move easily from 4 to 16 by grouping in 2s. You see what I mean? All right. As long as you have this power relationship. If you don't have the power relationship, it won't work. All right. Here's another example of converting from binary to hexadecimal. So base 2 to base 16. 2 to the power of 4 will give you 16. So that means that you have to group in 4s. This is because each group of 4 binary digits represents one hexadecimal digit. So group in 4s. Here's one group, put it down. All right, here's the next group, put it down. If you had another number here, you would just imagine those zeros. You can have as many zeros as you want to on the side. Okay, so this directly converts to 12. Okay? Oh, sorry, it directly converts to 11, which is B. This directly converts to 10, which is A. And so you would put A and B. So this number in base 2 is AB in base 16. So what about converting decimal to other bases? Okay, so now if this doesn't, if you don't have if you don't have this power relationship, if you can't, right? If you can't get this power relationship, then you might have to convert from decimal to other bases. And there is an algorithm for doing this, although it's you might not like it because it's long division. It's taking you back to long division. I don't know if many of you liked long division before when you were in school. When you were asked to divide different numbers, you would often use long division to do that. Well, here we're going to be doing the same thing, and there's a beautiful mathematical understanding here of why this works, and we'll discuss it. But let's just start with the algorithm first. So to convert a number in base 10 to other bases, right? You have to have that number, and you're converting from one number to the other while the quotient is not 0. Okay, you're gonna divide the decimal number by the new base, make the remainder the next digit to the left in the answer, and replace the original decimal number with the quotient. So we'll look at this. We'll look at this in an example. So before we look at it in an example, let's understand why it works. So remember what we're doing. Everything we do in number system has to do with this positional notation formula. And so we can write out any decimal number in positional notation formula and expand it in terms of the new base r. Okay, so here you go. This is the new base r expanded as a decimal number. Then all you would need to do, we remember what we're after. We're after this. If we can get this out, then we would have the next digit to the left as the answer. So how do we get this out? It's easy. We just need to get it. We just need to get it as a remainder. Okay, so what do? We divide by r, and if you divide by r, that means you will get this out as a remainder. So divide the base by r. Okay, so you're going to n divided by r, divide this all by r. Okay, it cancels everywhere. And your remainder is d1. Just falls out. Okay, that's your d1. Simple as that. That'll be the first digit. Then you repeat it, and then you get your d2. Then you repeat it, you get your d3, and so on. So this is actually the beautiful. If you understand how this works, it'll make it a lot easier for you to be manipulating this formula. Okay, so let's see this in action. So what is 1988 in base 10, right? In base 8. So we're converting from base 10 to base 8. Right. We already know how to go from base 8 to base 10. Okay, from the previous lecture I showed you how to convert any base to base 10 by just using the positional notation formula. But now what we're doing is the reverse. We're dividing by the base to get out the remainder. And the remainder is what we're saving. I think many of you might have to watch this lecture twice because you'll have little revelations after you watch this, and then you'll put it all together afterwards. So let's first look at this number, right? We're converting it to base 8. So here's the number. We divide it by 8. We do long division, okay? Long division. This here is your quotient. This is how many times 8 goes into this number. 248 times. And here's your remainder. So this becomes our d1, okay? Goes here. This is our d1. Then our quotient becomes the new number, okay? Relating it back to the formula algorithm. Make the remainder the next digit on the left. Replace the original decimal number with the quotient. This is where we are now. That becomes 248. Divided by 8. How many times does 8 go into 248? Use your long division. It goes 31 times with a remainder of 0. And that becomes our d2. Okay, the quotient now becomes the next digit, the next value. Divided by 8. How many times does 8 go into 31? 3 times, remainder 7. That becomes d3. Okay, we still haven't reached 0. Remember, we only stop this when we get a 0. That's what our algorithm says. Let's go back to our algorithm. While the quotient is not 0. Then we ask ourselves, how many times does 8 go into 3? It doesn't. With a remainder of 3, and that becomes our third one. So this, if this number was in base 10, this number is in base 8. And we can see it's in base 8 because it has the alphabet from 0 to 8, 0 to 7. There's no 8s or 9s or A's or B's or anything else. This is a direct conversion. Well done. You have now converted a decimal number to octal. Let's try it again in hexadecimal. Same procedure. We have the number in base 10. We're converting it to hexadecimal. How many times does 16 go into this number? It goes in there 222 times with a remainder of 15. 15 has a name in hexadecimal, and that name is F. So that becomes our first D1. Then we take our quotient 222. How many times does 16 go into 222? 13 times, remainder 14. 14 has a name. Its name is E in hexadecimal. If you don't know what I'm talking about, have a look at the previous lecture. How many times does 16 go into 13? Because we move the quotient across. And that is, it goes, well, 16 can't go into 13, so that's 0 times remainder 13. 13 has a name, it's D. So if we convert this base 10 number to hexadecimal, we'll get DEF. Well done, you've converted a decimal number to hexadecimal. If you've forgotten how long division works, there are many tutorials online, but it's just a simple procedure. So at this point now, you can convert any base to base 10. You can now convert any base, any value in base 10 to any other base. So you can go one to the other direction and so on, right? You can move from one to the other. And also if there's a special relationship, a power relationship between the bases you're going to and from, then you can even get there quicker by using groupings. So by this slide, you should be able to convert from any base to any base. Yeah, from any base to any base. By using long division or grouping or converting first to base 10 and then going to another base. So using base 10 as a proxy. Yeah, all right. Let's now look at fractions. Okay, so up to this point, you can deal with integers and you can do anything with integers. You can represent a value in any base. You can do arithmetic in any base, subtraction in any base. Some of you might be thinking about multiplication. Well, it's the same thing as previous lectures. As previously in base 10, your multiplication is also identical. But I'd like to give you an example of a multiplication operation, but I'll do that in the tutorial. The main thing is to understand here that at this point you can convert between bases and also count in any base and do operations in them. So from now, let's now focus on fractions. So let's look at representing fractions in base 2. So if we were to represent a fraction in base 2, let's say we're representing a number. And we've given the number and we now want to represent it using the positional notation formula, then all we've got to do is extend our formula. Okay, great. So we know what our formula looks like. It says, okay, well, you've got you've got the number dn multiplied by the base to the n minus 1 plus dn minus 1 multiplied by the base n minus 2 plus dot 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 d2 minus r to the power of 1 plus d1 multiplied by r to the power of 0. And then you have the radix point, right? This is all we used to see before, but now we can extend it. Here's the radix point plus. Now this is the digit on the first digit after the radix point. We call it d minus 1. It's position minus 1 multiplied by 2 to the minus 1 plus d minus 2 multiplied by 2 to the minus 2. That's r to the minus 2. This was a base 2 value. So thus, binary, this simply means this. To convert it to base 10. Well, this side is easy. This is simply going to be 1 multiplied by 2 to the power of 2 plus 0 multiplied by 2 to the power of 1 plus 1 multiplied by 2 to the power of 0. Dot, that's where the dot goes. 0 multiplied by 2 to the power of minus 1 plus 1 multiplied by 2 to the power of minus 2 plus 1 multiplied by 2 to the power of minus 3. Okay, minus 3 is the same thing as this written as a fraction. And if you add it up, it gives you the number in base 10. Ta-da! You now know how to convert binary fractions to base 10. So you can now do the same thing with this. Convert this hexadecimal fraction to decimal, aka base 10. How do you do it? Well, you simply say a, which is 10, multiplied by 16 to the power of, and you understand, right? So the first one would be 16 to the power of 1, then it'll be then it'll be plus 5 times 16 to the power of 0 plus f, and f, remember, is 15 multiplied by 16 to the power of minus 1 plus f again, which is 15 multiplied by 16 to the power of minus 2. So that's all you're doing, and you'll get this answer. So this is how you can convert hexadecimal to decimal. So let's now talk about converting fractions. So suppose I give you a fraction in base 10, and you want to convert it to another base. Okay. This is kind of exciting if you think about it, and it's not that difficult, but it's the same principle. So you multiply the decimal part of the number by the new base. Okay, then you're going to get an integer part and a decimal part. The integer part is the next digit to the right of the answer. Okay, and you replace the original decimal number with the fractional part. And you just continue in this way, multiplying out until, well, continue until, this is fairly open. You might continue until forever, because it could happen that your base 10 value gives you a recurring value in another base. It might happen. And if it does, then you would notice it, because you'll be noticing that you're going in circles. So let's have a look at this in practice. Oh yes, before we look at it in practice, we first need to know what we're doing. So as before, we will use the positional notation formula as a guide to see where we're going with this. So this all looks the same. Okay, we know what that looks like. Okay, converting fractions. The whole number part, we've done it already many times before. All right? Okay, so we're only focusing on the values after the radix point. So for example, if it was 1.001, then you just focus on the 001, you ignore the 1. You ignore the digit to the left of the radix point, and you keep the digit to the right of the radix point, right? So you throw this part away, you know how to handle that, you've done it before. So keep this part here. All right, so to get the first digit out, that is our d minus 1, all we've got to do is multiply it by the base. Multiply it by the base, as our algorithm tells us, and it'll flush out this d minus 1. And we can take that and save it somewhere as our first value. Okay? And you do the same thing again. You remove this d1, you keep only the radix part, and then you multiply again by 2, or whatever base it is in, that you go into. Then you flush out d minus 2. You do the same thing again, and you flush out d minus 3, and so on. And by doing this, you are extracting out the decimal one by one. You're extracting out the digit one by one. So let's do this as an example. So let's convert, let me show you an example. Okay, great. I think we should do it all. We should just do an example so you get the hang of this. So let me try to open up Microsoft Word. So I think that'll be the best place for me to write, since I don't have one of those fancy pen thingies. Okay, I'm making this a bit bigger. Okay, I think it'll be better if we put this in a table. It'll make it a lot easier to see. Okay, gonna make this big so you can see it. Okay, let's make this a bit bigger. Font. Okay, and let's insert a table, a small table like this. Okay, great. So what are we trying to do here? Okay, so that you can copy this method and it'll help you understand what's going on here. So what are we trying to do here? Well, we're trying to convert the number 0.1, which is a decimal number. Okay, we want to convert it to binary and hexadecimal and octal. And I'll do it for you in binary, and you can do the rest. And here's the answers. All right. So let's do it for, we're converting now from base 10 to base 2. So the first thing you do is you put this number as a base 10 value in our table, 0.1. Okay, you multiply it by 2 because we're going from this to base 2. And then you get a number 0.2, which is our number in base, which is a number that we get from multiplying this decimal number into 2. Now remember what we said before. in the previous slide here, we said that we need to keep the radix part and we throw away the rest. We're only going to keep the radix part, and this D1 that we flushed out after multiplying it, okay, this is going to be kept, and the rest of it, so this is going to be kept separately from the rest of it. Okay, let's see how we do that. So that becomes 0.1 multiplied by 2, which is 0.2. Okay, so now we're here, this part of the step. Okay, we have now our d minus 1, it's this. So this becomes the first digit. So it becomes radix point 0. Okay, right. Then we take our minus 2 and we write it down as our next step. We're continuing in this way. So we're going to say times 2, which gives you 0.4. So we now keep this separate, that becomes our 0, okay, and this, the decimal part here becomes what we move here, 0.4, multiplied by 2, okay, where am I, okay, I think I have to go back to Word, yes, there it is. I think I'm going to need more space, so let's insert some rows below, okay, I hope you can see this. This becomes, divided by 2, it becomes 0.8 times 2. Okay, so 8 times 2, 0.8 times 2 is 1.6. Oh, 1.6. All right. Now remember, I said that we were keeping all the time. We were keeping this whole number. All right, we were separating it. We're keeping this 0 in the 0.4, we're keeping the 0 in the 0.8. Now we're going to keep the 0 in the 1 in the 1.6. Okay, and we have to write it in here as well. Then we're taking the 6 out again, so it becomes 0.6. All right, 0.6 multiplied by 2. Remember, we're separating it, then it becomes 1.2. Okay, 1.2, take out the 1, put out the 0.2 here, again, times 2. Can we see a pattern? Well, I've done this already. Okay, I've done this already, I've done this already, I've done this already. So the next number is going to be, well, we can just complete it. So it's going to be 0.4, which we keep the 0, put the 0.4 here, x 2 times 2. Then it's going to give you 0.8. Okay, okay, we do the same thing again. Times 2, which gives you 1.6. Ah, I see a pattern. So then I'm going to get another one. So when I do this again, I'm just going to put a dot, 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 because I'm going to get the same thing again. See, I'm going to separate it again. I'm going to get back to this step. All right, and then I'm going to go to this step. Then I'm going to go to this step. Then I'm going to go to this step. Then I'm going to go again, back here again. And so on and so on. I'm going to do this forever. Okay, so the next number is going to be a 1. What do I notice? I notice that this is recurring. See? It came here first, then it's again, then it's again, then it's again, and so on and so on. So after this 0, the first 0 is fine. But then the 0, 0, 1, 1 recurs. And so on and so on. So we don't want to write it out like that because that's just untidy. What we rather do is write the recurring sign on top, like this. Okay? But, as you can imagine, I don't know where's the symbol for that on the keyboard. So what I would rather do, and you can do this in your tutorials, is just put the recurring part in brackets, like this. And this is how you would be doing, this is the answer after the operation. Okay, so this is fairly simple. It's fairly simple, it's not difficult. Here you're removing the integer part. I can write it here, remove. Okay, you're removing the integer part. You remove the integer part and you keep the decimal for this section over here. And we continue to do this. And that's basically how you would do the conversion from base 10 to any base. So for hexadecimal, you would not be multiplying by 2. You'll be multiplying by 16. Okay? and you would do the same table, but you'd be multiplying by 16. The same table multiplying by 16. Just thinking how to delete this stuff. Okay, the whole table goes. You're going to do the same thing multiplied by 16. And so on. All right. So see if you can get these answers. And yeah, that's basically how you convert from base 10 integers, fractions to any other base. The whole number part is easy, right? If you add a 3.1 here, converting 3 to binary is simple. You would do it using the previous methods that I showed you. Right, that takes us to subtraction of binary fractions. So subtraction of binary fractions is also simple because it's exactly the same as the subtraction before, with the exception of now we've got this fraction part. And all we got to do there is just line up the numbers by their fraction parts so that the positions match, and then we perform the subtraction. So I'll say it again. We line up the numbers by their positions with respect to the rate x so that their positions match up, and then we can perform the subtraction. Okay, that's important. So if there was a missing number here, you would still have this. You would still have the rate x points lined up so that you match the positions. And then perform the subtraction as we've seen before, and your rate x point will just drop. Okay, great. So this brings us to the end of this lecture. It was a lot of information, and that's why I broke it up into 2 separate lectures. And I want you to please take the time to understand what we spoke about here, what is going on in terms of binary in computers. So this last slide is just talking about what a bit is. So you've heard the word bit before. It just stands for binary digit, and a byte is made up of 8 bits. And a bit is just that it's a variable that can take the form of a 0 or 1. And that's all it is. The number of bytes in a word determines the word length. So you've heard of the word length before. You might not know what it meant before, but all it means is it's the word length of the computer. It's you've heard of 64-bit machines. That just means that you've got 64 bits sitting together. They can represent a number. And 32-bit machines, it just means you've got 32 bits sitting together to represent a number. Obviously, you can guess how many objects, well, you can work out how many objects can you represent with 64 bits, or how many objects can you represent with 32 bits. But it's a conversation for another time in our lecture on data representation. So what should you be able to do at the end of these 2 lectures, this one and the previous one? Well, you should firstly understand the importance of binary digits in its representation. Of course, this has a lot to do with the hardware significance, right? The use of transistors to represent information. Remember that everything in the computer, all of the fancy colors and the pictures and the diagrams and the words and the cursive and everything is represented using numbers. And it's represented as a binary number in the processor. Okay, you also have to understand the positional representation of numbers in different bases. We spoke about this with respect to the positional notation formula. I don't really like learning outcomes with the word understand for obvious reasons, because we don't know how to establish that. But this is just so you have a checklist so that you know what you should be looking at. You should be able to understand the relationship between base 2, base 8, and base 16 numbers. These are all power relationships. But beyond that, base 5 and base 25, base 4 and base 16, and base 2 and base 256, and so on. You should be able to convert from base R to base 10. That means any base to base 10, as well as any, you should be able to convert to any base as well. So from any base to base 10, from 10 to any base. And finally, you should be able to do arithmetic in any base. So base 3 arithmetic, base 5 arithmetic, subtraction in base 6, division in base 7, and so on. You all should be quite comfortable doing things like that. Okay, I'm not going to be ridiculous in what I ask you to do, but I think basic subtraction and addition, multiplication should be something that you can do, very basic ones. Obviously, the understanding it is more important. Okay, so, and also remember when you're doing the assessments, if it's taking you too long to do a question, then there probably is a smarter way to do it, okay? I don't like to take up, I wouldn't necessarily, for example, okay, let's look at an example. If I ask you to convert from base 8 to base 16, okay? Right, there might not be a power relationship between 8 and 16. Okay, but there is a power relationship between 2 and 8 and 2 and 16. So you could, in that case, convert from base 8 to 2 to 16, and that'll be quick. Okay, but if you were to convert directly from 8 to 16 without a power relationship, then you would have to go from base 8 to base 10 using the positional notation formula, and then from base 10 to base 16 using long division. Now you tell me, I'm being rhetorical because this is pre-recorded, which will be quicker? Identifying the power relationship between 2, 8, and 16, or converting from 8 to 16 via base 10. I'll leave it to you to figure that out. My point, the reason I'm being rhetorical is because I don't want you to be spending half an hour converting between bases when there's an easier way. Because if you spend half an hour converting from base to base and you haven't identified the easier way, then that's kind of your fault for not knowing this well enough. Okay, thank you very much for listening to me go on for 45 minutes. I hope this was useful. Remember that it might feel overwhelming understanding all of these things from the comfort of your living room, maybe. But what's more important is voicing when you're having difficulties. And I think we have quite a few tutors this year to assist you. There are going to be small tutorial groups that you can use to bring up problems that you have, discussions that you'd like to. I love talking about this stuff, and the tutors do too. So, chances are there's many students in the class too who would love to discuss this with you. So, study groups are encouraged. Obviously, there'll have to be online study groups on these online forums while this is quite a difficult time, as you can understand. Yeah, so please take the time to prepare. Try to find something that works for you. I know it's difficult, and it's difficult for me too. I mean, I would love to be in front of you right now as your lecturer, teaching you about these things on the chalkboard, using exam. We could always just talk about this in consultations. If this was the olden days, we could have little private sessions of private classroom sessions, and that will be great fun, and you would learn a lot more, in my opinion. But this is what we're faced with, and we're going to have to just make the most of it. So please don't sit and struggle, or don't leave your assessments to the last minute. Open these things and discuss them with your friends, and I encourage you to work with people. Now, as long as you're not plagiarizing, I encourage you to talk to your peers about the work, and try to, as we would have done in our tutorials. I don't want you to miss it too much because it'll just depress you as it has depressed me. So try to make this work. Yeah, all right. Take care, everyone. Bye-bye.